In this video, we're going to talk about question number 4 from the free response questions on the 2010 AP Calculus AB Form B examination. And in this question, we have this graph. It says that a squirrel starts at building A at time t equals 0 and travels along a straight horizontal wire connected to building B. For time between 0 and 18, the squirrel's velocity is modeled by the piecewise linear function defined by the graph above. Question A says, at what times in the interval from 0 to 18, if any, does the squirrel change direction? Give a reason for your answer. We know that something changes direction if the sign on the velocity changes. So if the velocity goes from positive to negative, or negative to positive, that's a change in direction. Positive velocity shows that the squirrel is going away from the building. Negative velocity that he's going back towards the building. There are two places, right here at 9 and here at 15, where the squirrel changes direction. So he's going away from the building for the first 9 seconds, and then he switches direction, and now that it's negative, he's going back towards the building, and then he switches again and starts going away from the building again. So for part A, my answer is at t equals 9 and t equals 15, because velocity changes sign. That's really all we need to say. We don't have to explain to the AP readers why a change in the sign of velocity corresponds with a change in direction. They just need to know that that's what makes that true. So the squirrel changed direction at time equals 9 and time equals 15 because velocity changes sign. That's part A. Done with that. B, at what time in the interval between 0 and 18 is the squirrel farthest from building A, and how far from building A is the squirrel at that time? Well, using our answer from the last question, we know that he's getting farther and farther away from the building for the first 9 seconds, and then because velocity becomes negative, he's going back towards the building for the next 6 seconds, from 9 to 15. And then again, he starts going back away from the building, but because we can see that here he's going back towards the building for 5 seconds at a speed or at a velocity of negative 10 units per second or hour. I'm not sure, they don't give us units here. And then when he turns around, he only goes back away from the building for a total of 3 seconds. So clearly he has not yet accounted for how far back towards the building he went. So he is farthest away from the building at time equals 9, because after there he goes back towards the building, and then even at the end when he does start going away from the building again, he doesn't make up for the fact that he went away for a little while. So for part B, we'll say at time equals 9. Now, the second part of the question is, well, how far away from the building is he? And to do that, we just have to look at area, because this is a velocity curve, and, oops, I didn't want to do that. This is a velocity curve, and since it's a velocity curve, the area under that velocity gives me the displacement, or how far away I am from where I started. So we just need to find the area under this trapezoid, and so my distance will be d is equal to 1/2 base 1, which is 9, plus base 2, which is 5, times the height, which is 20. Multiply that all out, and you're going to get 140 units away. So we'll say units from building A. Okay, so that's part B. They don't really ask for a justification here. They just want to know how far it is away. We know why that is the distance, but they don't ask us to explain that this time. Oops. Let's move that out of the way. And that got attached here, so let's see if we can just, well, okay. Let's go on. Now, actually, let's bring this back here. Whoops, 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 whoops. We're in some trouble. So, this was 140 units. Now, in part C, we have to explain the total distance the squirrel is away from, or I'm sorry, the total distance the squirrel travels. So because they're talking about the total distance that the squirrel travels and not how far away from the building he is, we don't need to worry about the fact that this distance here, this time he's going back towards the building. It's still distance that he traveled. He traveled 140 units away, then a certain number of units back towards the building, and then he went away from the building again. But I don't really care about which direction he's going if I just want to know the total distance he traveled. Not how far away from the building he is, like in part B, but the total distance that he traveled. If we already know that this area here is 140, we can use trapezoids again to figure out that this is 50, and then this area here is 25. So for part C, we're just going to add 140 plus 50 plus 25. Again, those are all just adding these three areas up, and we get 215 units. And again, it's very important that we understand that here they want the total distance traveled and not how far from the building he is. If they wanted how far from the building he was, we'd have to treat this 50 as negative because he's going 50 units back towards the building. Okay. But that's part C. Let's move on to part D. In part D, it says write expressions for the squirrel's acceleration, a of t, velocity, v of t, and distance, x of t, from building A that are valid for the time interval from 7 to 10. So first of all, we notice that we're only talking about going from 7 to 10 or along this linear section here. Now because this is a graph of v, to find acceleration, which is the first thing they want me to find here in part D, I know that acceleration is just the rate of change or slope of the velocity. And because it's linear, I know that my a of t is just going to be, my a of t is just going to be the slope of the velocity. And since it's linear, I just use my regular slope formula. So I'll do 20 minus negative 10 over 7 minus 10. And when we simplify that, we get that a of t is equal to negative 10. So a of t does not depend on my time for this interval here. A of t just depends on, or a of t is constant in this linear section here. Of course it changes because the slope changes from positive to 0 to negative to 0 to positive to 0. All they want is this section here where we have a slope of negative 10. So that's all we need. And that's a of t. Now v of t, again, this is a graph of v, and this section is linear, so I just need to know the coordinates of this, or the equation of this linear section here. So for v of t, we're just going to use some point slope form to start, and so I'm going to say y, I'm going to start with y's here, y minus 20, so that's the y-coordinate of my 1 point, is equal to the slope, negative 10, times, I'm going to use t because that's what they're using and not x, t minus 7. And typically you could leave your equation like this, but they do want it to look like v of t, so I'm going to get y by itself and then turn it into a v. When I get y by itself, y equals negative 10t, distribute there, and that would be plus 90. So that's my equation for v. That's the equation of that linear section. So v of t equals negative 10t plus 90. Okay. So that's a of t, that's v of t, and now I've got to find x of t, which is my distance from the building. Now, because we have velocity and they want us to find distance from the building or position, I should immediately think, well, that's going to be an integral. So I'm going to integrate my v of t. So x of t should equal the integral of v of t dt, again, because distance from the building is same as position here. The integral here, we just need to use the power rule for integration or anti-differentiation, and we get, again, this is going to be the integral of this v equation that we just found, so that's going to be negative 5t squared plus 90t, and then because it's a an indefinite integral, we don't have limits here on our integration or an interval, I've got to remember my plus c. I don't want to leave a plus c in my final equation though, so I need to know a point. I have to know a position at a specific time so that I can plug in and solve for c. Fortunately, we already solved for the position or the distance from the building at time t equals 9. We did that in part B. And 9 is in between 7 and 10, which we're talking about. So I can plug in my answer from before for x of 9. The position when t equals 9 was 140. Oops, forgot my 1. So that means that 140 is equal to negative 5 times 9 squared plus 90 times 9 plus c. And yeah, those numbers are a little bit big, but you can solve that even though this is the non-calculator section. You can solve that, and for c, you'll get negative 265. I'll leave you to work that out. So now I have my final equation for x of t is negative 5t squared plus 90t, oops, not leaving myself enough room here, minus 265. And that's my equation. So now I'm done with part D because I found a of t, v of t, and x of t. And that's how I would do number 4. All right.